It's time to start bringing this unit to a natural close. We've learned a lot of concepts, so what we'd like to do now is we'd like to kind of tie them all together and sort of wrap everything up. So we've kind of talked about waves behaving like particles. So, we have like light behaving like a particle. But we haven't talked about things that are traditionally particles, say electrons, behaving like a wave. And this was exactly the radical idea that was proposed by a gentleman named Louis de Broglie in his PhD thesis in 1924. So he basically argued from a symmetry point of view, well, hang on a minute, if we can treat waves like particles, we should be able to treat actual particles like waves as well, like it has to go both ways. Now, people thought that was a little bit nuts, like the people on his thesis committee, but somehow Albert Einstein got a hold of de Broglie's thesis and said, like, this work is miraculous and it has a lot of scientific merit. So de Broglie got his PhD. So, as I mentioned, de Broglie basically argued from the concept of symmetry that if we're going to treat waves like particles, we have to also treat particles like waves. And the photoelectric and Compton effects really helped to solidify this because it showed that light had particle-like properties, but it also had wave-like properties. And essentially this whole dichotomy that we have of wave and particle, this is what we refer to as the wave-particle duality. So now we want to kind of finalize, is light a wave or is it a particle? And here is the answer. It's neither of them. It's both at the same time. Light is both a particle and light is also a wave. How we observe the light, whether we observe more of a particle form or a wave form, it depends on our interaction. But light is both particle and wave together. So that's the kind of conclusion of which model is the better one. Neither of them. We need to take both models together. So de Broglie kind of took this idea of wave-particle duality and he wanted to relate particle properties with wave properties. So he came up with this following formula, this lambda equals h over p. So this is referred to as the de Broglie wavelength formula. And again, it relates it kind of relates waves and particle properties because wavelength is something we generally associate with waves, and momentum is something that we associate with particles. So we have kind of wave and particle characteristics joined together. So lambda is going to be that wavelength, h is going to be Planck's constant. Again, we have to use this value in joule seconds. We cannot use the electron volt seconds one. And then the momentum, kilogram meters per second or Newton seconds, whichever you prefer. So if you happen to be using lambda equals h over p, this invokes physics principle number 9. This invokes the whole concept of wave-particle duality. So let's have a look at this. So let's calculate the wavelength of a person. So a person who is 100 kilograms, they are going to walk with a speed of 2 meters per second. So let's see. We got lambda equals h over p. Now for a person walking at a speed of 2 meters per second, we know our definition of p is just going to be mv. So we have this h over mv. So let's find this wavelength of a person. So we got 6.63 times 10 to the minus 34 joule seconds. We have that mass, or sorry, not the mass. We're going to put the mass of the electron. So we got that mass of 100 kilos for the person. We'll scratch that out. And then we have their speed of 2 meters per second. So you can probably already see this wavelength is going to be really, really, really small. So what we're going to get is we're going to get an astoundingly small 3.32 times 10 to the minus 36 meters. So a 100 kilogram person walking at 2 meters per second, they have a wavelength of about 3.32 times 10 to the minus 36 meters. So that's really small to be the understatement of the year. You are not going to really notice that. So a person, even though they technically have a wavelength, they don't really exhibit wave characteristics. Like their principal wave characteristic of a wavelength is astronomically small. So treating people like a particle, not really, not a bad thing. So this whole wave-particle duality, people didn't really buy into that at the time. Like people thought it was kind of nonsense, and Einstein himself, he thought wave-particle duality was actually a fault of quantum mechanics itself. Like he thought there must have been a way to fix that. Other scientists like Niels Bohr, he just kind of said like whatever, like deal with it, and he learned to live with it. And the reason that we find it to be bizarre is it has to kind of deal with our mindset, like the Western mindset of thinking. We are so used to, in science, of having a definitive answer. Like, you do X, you always get Y. So we're used to very black and white thinking in science. Wave-particle duality is very much a shades of gray kind of thing. Like, it's kind of a little bit of both sides. So we kind of have a hard time thinking about that from that point of view. And the other thing is, we're still very much entrenched in classical physics. Like, most of the physics you've learned has been classical physics, so you're trying to look at quantum mechanics from a classical perspective, but you can't do that. It's kind of messing with your brain. So if wave-particle duality and all this quantum stuff kind of rattles the brain, you're on the right track. Niels Bohr said if quantum mechanics doesn't confuse you, you're not doing it right. So if it's confusing, you're on the right path. So the last thing we just want to kind of tie into with this wave-particle duality has to deal with the momentum of a photon. Because the photon, it's going to be the carrier of our electromagnetic force. Now, you also know that a photon is massless. So if you say to me, well, wait a minute, it's massless and you want us to calculate the momentum. Well, mass is 0, P is 0, because we know P equals mv. Good try. The answer is no. P equals mv is not going to work for photons. We have to actually use something else. Instead of relating momentum to mass, we're actually going to use the relationship between momentum and energy. That relationship will allow us to determine the momentum of a photon, because we know photons have energy. And this is basically meant to establish that energy and momentum can be linked. So the equation that we have here is that E equals Pc. E is going to be the energy of our photon in joules. This E here, this is still the hf or hc over lambda that we learned earlier from Planck's equation. P is going to be the momentum of the photon, again in kilogram meters per second or Newton seconds. Yes, I realize having something massless in units of kilogram meters per second, it is bizarre. It is what it is. And then C is the speed of light in meters per second. The big caveat though, E equals Pc is only for photons. So we wouldn't be using that for anything like particle based. Like, if you're looking at we want to be very careful with this equation here. It has a very limited application. So let's look at this in an example really quickly. So we have the momentum of a dental X-ray photon. It's 3 times 10 to the minus 23 kilogram meters per second. We would like to determine the minimum voltage that is required to create this X-ray in a cathode ray tube. Alright, so for us, we know that the dental ray photon, its energy is going to be Pc. We also know that when we're dealing with voltages and stuff, voltage, the energy related to, we're looking at potential energy here. We know that the energy is going to be QV. This is our definition for electric potential and electric potential energy. So the electric potential energy is going to be QV. So that energy of the photon, that is going to be converted into electric potential energy. So what we're really going to do is we're going to link these two ideas together. What we're going to say is we're going to say that Pc is equal to QV. And we are interested in finding the minimum potential difference. So we're going to have Pc over Q. Now, the big problem, we know what P is, we know what C. We may have a bit of an issue. What is Q? Well, I probably should put this in the question, but an X-ray is usually formed from high energy scattering of electrons. Or it's basically formed from like high energy, or actually, sorry, let me rephrase that. When we're dealing with X-rays, we're kind of still dealing with a bit of a Compton scattering, like we're dealing with high energy electrons in this case. So when we have X-rays, we want to say we're dealing with high energy electrons. So these high energy electrons are going to produce X-rays. So high energy electrons producing X-rays, that means that we are going to use Q as the elementary charge. So I probably should have put this information in the question, but it happens, I forgot. Alright, so we have the momentum, that 3 times 10 to the minus 23 kilogram meters per second. We have that 3 times 10 to the 8 meters per second, and then we're going to divide that by Q, the elementary charge. So this is going to give us the potential difference required to actually create this X-ray. So if we do this, we are going to get, let's see here, we're going to get about 5.63 times 10 to the 4 volts. So this potential difference applied, this is going to create an X-ray photon with a momentum of about 3.00 times 10 to the minus 23 kilogram meters per second.